Now let's answer the question, what is the direction of the magnetic force if the wires carry currents in opposite directions? So let's represent the current in wire 1 as going straight up, I1, and let's represent the current in wire 2 as going straight down, I2. Now, we're going to do the same work as we've done before. Let's find the magnitude of the magnetic force on wire 2 due to wire 1. We already know that that is going to be equal to the current in wire 2 times the magnetic field due to wire 1 times the length of wire 2. So the magnitude of the magnetic force is going to be exactly the same as we found in the first part of this problem. It's going to be equal to mu naught over 2 pi r times the product of the currents and the length of the wire. The work is no different. Same distance, same length, same currents, or at least the same magnitude of the currents. The magnetic force will be exactly the same. But what about the direction of the magnetic force? Well, let's go ahead and look at that. So from part A, we already applied the right-hand rule. And when we applied the right-hand rule, we saw that the magnetic field lines form concentric circles around the current producing the magnetic field. And these concentric circles have a certain orientation given to us by the right-hand rule. And at the location of wire 2, we know that the magnetic field is going to be uniform on wire 2 and pointing straight away. So here we have the current going down, so the displacement differential is going down. The magnetic field due to wire 1 is going straight away from us. Now let's apply the right-hand rule to figure out the direction of the magnetic force. The direction of the magnetic force will be given to us by the direction of the result of this cross product between the displacement differential and the magnetic field due to wire 1. So again, we're going to place the fingers of our right hand in the direction of the first vector. We're going to face our palm in the direction of the second vector. And where our thumb ends up gives us the direction of the magnetic force between the two. So when we do that, my right hand, when I face it down, look, when I do that, my right hand, when I face it down, will have its thumb pointing to the right. And because the thumb of my right hand is pointing to the right, that means that the magnetic force on wire 2 is to the right due to wire 1's magnetic field. And from Newton's third law, we could say that the magnetic force on wire 1 due to wire 2's magnetic field is also pointing away from wire 2. So this magnetic force is repulsive. So what we can conclude here is when two current-carrying wires that are parallel, if they carry currents in the same direction, the magnetic force is attractive. And if they carry currents in the opposite direction, the magnetic force between them is repulsive.